So the topic for today's webinar is about StarRocks. What is StarRocks? Features and use cases. Hello, everyone. I am Sita Shen. I am the product marketing manager at CelerData, and I'm also a StarRocks contributor. So first, let's go over the agenda. What we're gonna talk about today. So first is a high-level introduction to the StarRocks project, right? And then we're gonna dive into StarRocks architecture and how StarRocks can be deployed and used for different kind of use cases, right? And then we're gonna dive into the actual use cases. First is real-time analytics, and the second is data lakehouse analytics. So for each use case, we're gonna talk about the challenges of that use cases in the industry, right? And how StarRocks' unique set of features can solve or alleviate those challenges, right? And then we're gonna take a look at some actual use cases from or success stories from actual StarRocks users, right? Industry leaders. So first, let's talk about StarRocks. StarRocks is the open source Lakehouse SQL engine, right? And a challenge or a problem that we see a lot, especially in the data analytics field, is that a lot of problems can be solved on the database side or on the infrastructure level side. But instead, vendors are forcing the users to build costly workarounds, data pipelines, to work around those problems, right? So the StarRocks project is born, with a vision to utilize its extreme performance, so the StarRocks users don't have to perform those workarounds and build those data pipelines which makes data analytics easier and more accessible for everyone, right? StarRocks is available, open source, available on GitHub, and is also an Linux Foundation project. As of February 2024, it's accumulated 7.3 thousand stars, almost 16,000 commits, and 324 contributors from around the world, right? It has been adopted by industry leaders such as Airbnb, Celonis, Tencent, MiHoYo, Trip.com, and more, a lot more, right? And you can learn more about StarRocks, in two links. The first is the GitHub repo, and the second is StarRocks homepage. And then let's talk about StarRocks architecture and how StarRocks can be deployed, for your use cases, right? A lot of you are probably StarRocks users. You probably know that StarRocks can be used first as a data warehouse or as a data lakehouse query engine, right? As a data warehouse, StarRocks has a very simple architecture when compared to other similar solutions. It has no external dependencies, only has two kinds of processes, FE and CN, right? FE is the catalog manager, is in charge of, managing the metadata and generating query plans, right? And CN is a kind of like the muscle of the StarRocks cluster, is in charge of, scanning data from external storages and caching data and actually performing the query execution, right? As a data warehouse, so StarRocks persists the data for you, right? So the data is persisted within StarRocks with StarRocks' own file and table format, right? StarRocks' own table format with StarRocks tables, right? And the formats are built specifically for high performance workloads, right? It supports real-time mutable data. You can use StarRocks with data updates and get sub 10-second data freshness, right? And its own storage feature, a lot of them are built for extremely high concurrency, low latency, customer-facing workloads, right? And StarRocks also features an storage and compute separated design, right? Or call it a shared data design, where instead of the data persisting inside of each node, it is persisted in remote storage, still in StarRocks' own file format though, right? In a cloud object storage, such as AWS S3, right? And the built-in cache, memory and disk-based caching is on CN, and that's for query acceleration, right? So you can get the same performance as it would, like a shared nothing architecture, right? A shared data architecture is great for the cloud. Why? Because you can scale your compute and your storage independently, right? So there is less waste of resource, and also because you're not really persisting any data within your nodes, your compute nodes, so you can evict any nodes you have when the traffic is low without actually losing data, right? So scaling is great in this kind of architecture, right? And also StarRocks is standard SQL compliant, as well as it supports Trino dialect, so you can keep all of the BI tools you love, right? As long as it supports standard SQL or MySQL protocol. And also StarRocks can be used as a Lakehouse query engine, right? So the difference between this and the data warehouse architecture is that instead of persisting data within StarRocks, it's persisted in an external data lake or data lakehouse system, open lake system, right? In open lake table formats and open standardized file formats, right? And table formats such as Delta Lake, Apache Iceberg, Apache Hudi have open standard file formats such as Parquet ORC, even CSV, right? And StarRocks is built to deliver data warehouse-like performance on the data lake, so you can unify even the most demanding workloads on your data lake. So how does StarRocks address the denormalization challenge in real-time analytics? So first, to do real-time analytics with StarRocks, right, you would ingest the data into StarRocks storage engine, right, and utilize the strong StarRocks file and table format, right, to perform, fresh mutable data, right, fresh data updates, right, and to address the denormalization challenge, it's actually quite simple, to do what? Just to run really fast joins, right? StarRocks has probably done all of the possible optimizations you can think of, for a database or data warehouse, right? C++, SIMD, optimization, columnar storage, vectorization, and a bunch more, right? We're gonna get into them later in this slides. Basically, to run on-the-fly join queries so fast that you can ditch, all of your denormalization pipelines, right? But just how fast StarRocks join is, first show some numbers here, right? So this is a SSB benchmark test, a comparison between StarRocks versus ClickHouse and Apache Druid out of the box, right? So first you see, on the right-hand side, there is flat and multi-table, right? SSB originally is a multi-table test with many tables and perform join on the fly, right? Test the join performance. But ClickHouse created a variant of that benchmark test, basically to perform a denormalization on all of the tables, all of the SSB tables beforehand. So during the actual benchmark, at query time, there is only on-the-fly aggregations, but there is no on-the-fly joins, right? And so here, everything with a flat is run on the flat table, with the denormalization, and everything with multi-table with StarRocks is run on the original multi-table schema, right? So we can see that here with flat, StarRocks is a lot faster than Druid and faster than ClickHouse, right? But the key here is that StarRocks multi-table is even faster than Apache Druid's flat table performance, and it's almost as fast as ClickHouse single table performance, right? And join is probably the most expensive thing you can write with a SQL script. So this says a lot for StarRocks join performance here, right? So the question to ask is, how does StarRocks get this amazing join performance, right? And in this session, we're gonna dive a little deep into the StarRocks features that enable this join performance, right? So before we actually dive into this, let's talk about how a SQL query works, right? A lifetime of a SQL, right? The SQL first hits the network layer and gets sent to the query planner, and the planner analyzes the SQL and generates a physical distributed plan for the execution engine, and the execution engine scan data from the storage and according to the distributed physical plan and actually execute the query and get the result returned to the network layer, and then the user see the query result, right? And from this, there are a lot of things that can be optimized, right? SQL Planner and how a SQL is executed, right? So these two main parts. So first, let's talk about StarRocks query planning, right? It uses a cost-based optimizer, and why. So optimizing a query, planning a query is a very challenging task because the search space of possible ways of executing a query is enormous, right? Especially when you consider join operations and complex aggregation operations, right? With join reordering and the type of join algorithms to pick, for each single instance, and distributed join strategies such as broadcast join, or we do a shuffle join, right? And aggregation methods, those are many things we can pick. So the search space is enormous, right? And the difference between optimized plan and inoptimized plan can be several orders of magnitude big, right? And StarRocks incorporates its own cost-based optimizer. So what it does is that it collects statistics directly from the data you store, right? And estimate the cost of each potential plan and select the best one according to the cost that's being calculated, right? And it's natively built and deeply integrated with the execution and storage layer of StarRocks. It's really impossible to get a query planner or a query optimizer right the first time, right? Thank God StarRocks is open source, so we have a ton of users to iterate this feature for the past few years, and now is really mature and is able to deliver this amazing join performance for all of the StarRocks users. To demonstrate what StarRocks Query Planner can do, our cost-based optimizer can do, here's an example, right? Data pruning. So running an OLAP query, one important thing is to minimize the data that's being scanned, by the execution engine, right? This does many things. So it puts less stress on the storage device, and it minimizes the network of transferring the data, and also takes stress off the CPU because the CPU ultimately process a lot less data, right? In this example, we use a feature called a global runtime filter in StarRocks that just does this data pruning specifically, right? Let's talk about this through an example. Let's take a look at the query here, right? It's a join between the dimension table and the fact table on a predicate that's from the dimension table price column greater than 100, right? Let's say without the fact table, knowing about this predicate, it scans around 1 billion rows of data, right? But with this information, it can scan a lot less. Let's say 1 million rows, right? So how do we get the fact table, all of the nodes that contains the fact table to know about this predicate information, right? So the first way, if the price column is also in the fact table, it becomes a lot easier, right? Just send the predicate over and call it a day, right? But what if the price column is not in the fact table, right? What StarRocks does is generates a CMD Bloom filter and send it to all of the nodes that contains the fact table in it, right? But the challenge is the filter actually worth the network cost, a network overhead of sending this big Bloom filter over, right? And this is a decision that our cost-based optimizer make, and it figures out for you, right? So actually based on the actual statistic of your data, because this decision is really case by case. It depends on the distribution of your data, and it also depends on the query that's being run, right? So and this is something that only the cost-based optimizer can do. And enough of the query planning part. Let's talk a little bit about query execution. So first, let's talk about this on a higher level, right? The compute architecture of different systems. So I categorize that into kind of three main categories. So first is like a scatter-gather compute architecture. And this is widely used by a lot of the real-time OLAP database, OLAP data warehouse, right? For example, ClickHouse and Druid. So what this does is you have a main node and you divide your workload into your tasks into many subtasks and distribute them to your worker nodes. And after they're done, do a final aggregation at, like the bigger node. The problem with this is it's easily bottlenecks on a single node, right? It's really not suitable for joins and larger scale joins and high cardinality aggregations, right? And the second architecture is MapReduce. A lot of us heard of this, I'm sure. So MapReduce has a data shuffling service, right? So you can shuffle the data during query execution, right? So this does not have the single node bottleneck problem that ScatterGather has. But MapReduce was developed for long-running ETL jobs. So stability is a big concern, right? So the data shuffling service of MapReduce is disk-based. So all the intermediate results are stored to disk for stability reasons, right? So their wait time between tasks is very stable, but for very long-running ETL workloads, but it's really not ideal for low latency queries, right? And the last is MTPP architecture, right? It also supports data shuffling, but in-memory data shuffling, right? So it ensures scalability. Because it's in memory, the whole query process, the whole query execution can be run completely in memory. So it guarantees performance as well, right? So it's great for sub-second joins and aggregations at scale, right? So this is the architecture that StarRocks incorporates for sub-second joins and aggregations at scale. So to go into query execution, we want to talk about storage. StarRocks has a columnar storage plus fully vectorized OLAP operators. So instead of storing everything by row, everything is stored in column, right? Because in OLAP, just look at the SQL, everything is in column, right? And for a computer, for a server, running batch is always better than running small chunks, right? Row by row. So it's by running everything by batch, it's a lot more CPU cache friendly. And it's way easier to incorporate modern SIMD optimizations, right? I'll talk about in the next slide. SIMD optimization is basically saying that we process everything in batch, in bigger batch, right? And what this does, it's minimize the number of memory seeks, right? That's there. You can see that the image on the left top corner is without SIMD, and the other image is with SIMD, right? It's a lot less touch on memory, right? And StarRocks written in C++, so SIMD support is completely native, right? And this is actually why StarRocks relies on AVX2 instruction sets, right? Because of SIMD. Now we see a lot of theory, we see a lot of features, right? But how does this perform in the real world, in actual big systems? Can StarRocks users can actually go denormalization pipeline free? So the first example is Airbnb's Minerva metric management platform, right? Before they were using Druid, Presto, and Spark as the query slash processing layer, right? Because especially Druid cannot really handle multi-table joins at scale. So they really had to denormalize everything, every table. If it appears in the query, it needs to be denormalized, right? So this creates a lot of problem. So the biggest problem was actually flexibility for them. Every time they make a schema change on the original table, they have to backfill data into all of the big wide tables, denormalized wide tables, and that takes a very long time and consume a lot of resource. So a schema change with Druid, with this architecture, can take hours or up to days, which is really not acceptable for a metrics platform, right? And then they went to StarRocks. Because StarRocks can perform joins at scale, can actually do joins really well. The biggest change for them was denormalization once was a default, right? Everything denormalized. Now it's only done on demand for extremely demanding workloads. So this saved them a lot of waste of compute and labor of building those denormalization pipelines, also making everything agile, right? The schema changes does not take hours or days anymore, right? The second example is from Tencent Games. Tencent Games is one of the biggest gaming company in the world, right? They have big titles such as PUBG and League of Legends, right? So before, they're actually in an even worse case situation than Airbnb. Airbnb only does denormalization, but for Tencent Games, everything is pre-computed, including joins and aggregations, right? They actually pre-compute every single thing and use the TP database for serving, all of its dashboards, right? And also they had a separated real-time and batch pipeline, which is, just even more complex and expensive to maintain, right? After they make the switch to StarRocks, they can do on-the-fly computation now, right? So that's really good for self-service multidimensional analysis, right? You can, select a different column and get the result instantly without messing with the pre-computation pipeline, right? And with StarRocks handling both real-time and batch workloads, it greatly simplifies their data architecture as well. So how to get started with StarRocks as a data warehouse? So on the documentation, there are many ways. So the first is you can use Docker Compose with StarRocks and a local object storage menu, right? That's being built. That's already built, and you can see that on documentation. And there's also a Kubernetes operator, right? You can use, or you can use VM install, right? So bare metal. The next use case we're going to cover today is with data lakehouse query, right? Specifically, how to get data warehouse performance with StarRocks as your data lakehouse query engine, and the benefit of doing that, right? Before we actually dive into this topic, let's go over what is data lakehouse and the benefits that data lakehouse provides for the data users, right? So what data lakehouse is, it's basically the combination of the feature of data warehouse plus the open and standardized storage of data lakes, right? Open and standardized table formats as well as file formats. Having that, the immediate benefit is that you're able to unify all workloads on a single source of truth data with the data lakehouse architecture, right? As opposed to, for example, let's say you have a proprietary data warehouse, right? The amount of workload you can run on your data warehouse is limited by the data warehouse itself, right? maybe that data warehouse has a few connectors that can connect to other applications or compute engines or other, ML applications, right? But it's limited, nowhere near the number of workloads you're going to run with your business scenarios, right? But this is only doable through an open and standardized storage, right? That can connect to all kinds of different applications, right? And the benefit of having a single source of truth data is enormous, right? First, there's only one copy of data you need to worry about, and that significantly simplifies the data governance challenge, right? And also, there is only one storage you need to worry about and connects all of the applications to that one storage. And that simplifies the architecture, the data architecture as well, right? And overall, it greatly improves the cost effectiveness of your whole data architecture, right? Data Lakehouse is great, and a lot of people are using it. So the people are using it, they must be running all of their workloads on that one copy of data, right? But the reality is not really. See, a lot of users are still copying their data out of their data lakehouse, only for query acceleration reasons. The reason for that is external data lake query engines are really not performant enough to run all of the workloads that we're trying to throw at it, right? They're either first not optimized for high concurrency, low latency workloads, right? They're probably more optimized for batch ETL jobs that runs for hours, right? Or they're still on older technologies, right? They're not equipped with all of the crazy optimizations we can do with a modern query engine today, in 2024, right? Because they cannot really handle all of the workloads. As a workaround, users are still forced to move their workloads and the data to a high performance proprietary data warehouse purely for query acceleration reasons, right? This does solve the performance issue, but it introduces a lot more trouble than the good it does, right? First, you have to consider the cost of maintaining an infrastructure level software, right? Like a data warehouse. It's not only heavy, but it's also stateful, right? So maintaining that it's a lot of hardware resource and a lot of labor as well, right? And also you have to consider the cost of your data ingestion pipelines, right? Data ingestion essentially is writing your data from one format to another, which is an extremely resource intensive job, right? And maintaining the data ingestion pipeline can be very difficult because they tend to break, right? And there are a lot of pipelines you're trying to maintaining, if you're moving a lot of workloads, and that can be troublesome as well. It elevates a problem, right? And also there is challenges from schema design, a whole new set of schema design in your data warehouse, and matching that with your data lakehouse storage system, and that can be really labor intensive as well, right? And data governance, where you're basically duplicating your data, right? Just trying to keep your data in syncs between multiple systems, that can be a huge data governance nightmare, right? So this is very expensive. So what is the reason? So why optimizing data lake query is different, right? What are the specific challenges of fast data lake queries, right? The main cost of optimizing data lake query is the process of fetching data and metadata from your external data lake storage, right? First is the most obvious one is the network overhead that comes with it, right? Scanning the data lake and fetching the data out of the data lake and send it back to the query layer, right? That's a very expensive and time-consuming process. What makes it worse is that modern query engines, if it's designed to perform join and high cardinality aggregation, it has a shuffle service, right? So it's able to reshuffle the data between nodes during query execution, which uses a lot of network I/O, right? So this process not only itself is slow, but it actually can slow the query execution process as well, which is even worse, right? And also data lakes are known to be slower on slower storage devices, right? And unpredictable performance because many people are using it, right? So the performance can varies, right? And also data files can be unoptimized for query performance. It's very likely that if a data lake is not compacted correctly, there can be a lot of small files, right? And that is something that we cannot really control, for some cases, right? And that's horrible for data scanning, make it very slow, right? And this whole process is becoming an even greater problem because query engines execution runs so much faster now, right? The faster the query engine is able to go, the faster it executes, the bigger this problem is, right? And actually with StarRocks, because StarRocks execute queries so fast, even with the most complex complex query with a lot of joins and aggregations, this can still be a bottleneck. So solving this is absolutely the priority of getting fast data lake house queries. So how StarRocks accelerate data lake house queries? So first, StarRocks has a data cache framework, right? It's a hierarchical caching framework that's based on both memory and disk, right? So it does two things. First, it overcomes the unstable performance of data lakes, right? And then it tries its best to save I/O costs from fetching the data from external storage, right? Because if there's a cache hit, there's StarRocks doesn't really need to talk to the external storage, right? And save the network I/O. And also, StarRocks features an in-memory MPP architecture, right? It can do in-memory data shuffling, right? And this is great for low latency workload as opposed to those batch processing tools that stores all of the intermediate results to disk for better stability, right? For hours, for jobs that runs for hours, right? And StarRocks is also equipped with modern advanced system level optimizations, right? Its front end is written in Java. The query planning part is written in Java, but the CN, the compute node, the execution layer is completely implemented in C++ to fully utilize the SIMD instruction sets, which is really important if you are running a complex OLAP query, right? All of this combined and with a lot more detailed optimizations and features, getting data warehouse performance on the data lake house is actually quite easy. I'll show you some data like right now. This is an image already showed in the previous section. StarRocks itself can work as a data warehouse. It has amazing performance, right? And this is StarRocks as a data warehouse versus StarRocks as a lakehouse query engine. This is on the TPCDS 1 terabyte benchmark test, right? Hot queries, exact same hardware. One is ingested into StarRocks and one is, querying open standardized storage, open data lakes, right? StarRocks data warehouse solution is only 12% faster than the Lakehouse query engine, right? So think about it here. We're only giving up 12% of the performance. For what? For unifying all the workloads on one piece of data. And that's massive amount of gain, right? Then we'll show another benchmark between StarRocks and Trino, which is another popular open source query engine that's really good at connecting to a lot of data sources and perform in-place analytics without actually moving the data, right? And see how much faster purposely built Lakehouse query engine like StarRocks is faster than Trino, right? On the TPCDS 1 terabyte benchmark test, StarRocks is 5.5 times faster than Trino, like half a magnitude faster. right? These benchmarks and theories and features might sound good in theory, but how do they perform in actual production systems? Here I'll show one use case. This is ATRenew. ATRenew is a global recycle company, and they're in the environmental protection sector, right? So let's say if you want to recycle your old cell phone and recoup some of that money back, you would probably sell it to ATRenew, right? They have absolutely insane amount of data. There are hundreds of terabytes of data ingested per day, and they can store up to 5 years of historical data for some of their tables. And that results in a staggering 30 to 40,000 Hive tables. And query often scan half of the entire dataset, which make the whole thing even more challenging, right? Going for an OLAP database was not even feasible in the beginning when they designed the system because cost of storage would be just too expensive. Right, so they went for Hive as their data lake to store the data, and Trino as the query engine, right, does all of the query, right. But they ran into problems with Trino. Trino just could not handle the amount of data and return the result, required amount of time without blowing up the bank, adding way too many nodes, right. So they discovered StarRocks, and according to their own test on the TBCDS benchmark, StarRocks is almost 17 times faster than Trino under 20 concurrency. And in production, 80 of the queries experienced at least 2 times the performance gain. And that's even without turning on the StarRocks caching capability. Right. With that, it's going to be even a bigger gap between the two. Getting just fast raw query performance is good, but it's actually not enough for data lake queries, right? With sheer amount of data we have in the data lake, pre-computation, data pipeline with pre-computation is sometimes is absolutely necessary, to get good performance, right? Pre-computations are, denormalizations and pre-aggregations, right? Those pre-computed results stored there, so you don't have to do some of the computations on the fly, right? But existing ETL tools are not really optimized for modern query engines, for to do those ETL jobs, right? Here is an example. Let's assume you're a data engineer, right? You're maintaining some analytics service, right? And your data user identifies a slow query and he reports it back to you, right? To solve that slow query, you add a pre-computation pipeline, a pre-computation table, to your pipeline. That can be a denormalized table that joins a bunch of other tables together, right? But the pre-computation pipeline you just added will not take effect until the SQL is rewritten to point to the new table, the new pre-computed table you just created, right? And the rewriting SQL, this part is extremely time consuming and labor intensive, right? This actually forces the data engineers to figure out all of the data pipeline prior to developing, the client side application, aka writing the SQL scripts, right? So this end up being data engineers are building pipelines to generate tables that never get used because rewriting SQL is just too expensive. So when they plan a little more than they need, right? And also extremely lengthen the development cycle because the planning part is extremely time consuming, and ultimately you go to production a lot slower, right? And this is caused by query engines are running so much faster now, right? Like before, when query engines are slow, everything is pre-computed by default, right? So on-demand pre-computation is not really a need because there's not much things you can actually run on the fly. And now query engines are running so much faster, we can do a lot more computations on demand now when we compare 5-10 years ago, right? So a shift from pre-compute everything to on-demand pre-computation, this is the reason why there is is a big mismatch between the extremely high performance query engine like StarRocks and the traditional ETL pipeline, pre-computation ETL pipeline with Spark, like Spark like batch processing tools, right? The big mismatch there. StarRocks has a materialized view feature that enables on-demand pre-computation, right? So materialized view is a stored result of a query, right? And StarRocks materialized view has a unique feature that it can do query rewrite. The meaning of that is that because materialized view is also managed by StarRocks, so during a query, the query can be routed automatically to the most optimized, to the most suitable materialized view for query acceleration, right? So you don't have to rewrite the SQL yourself, right? And this one feature alone greatly enables on-demand pre-computation. What does that mean? Is that you can, with StarRocks materialized view, you can just query the original data schema, multi-table normalized schema by default, and use materialized view to solve any slow query you might have, right? And in practice, because of StarRocks' amazing performance, especially with multi-table queries, there's not that many materialized views you actually need to add to get good performance to eliminate all of the slow queries, right? I'm going to showcase this with another use case from Trip.com. Trip.com is a leading travel company, right? And Artnova is their kind of like a unified reporting platform. So all of their reporting workload, dashboarding workload goes through this, is powered by this Artnova platform, right? Before they were on a classic, my query engine is not fast enough. I need the data warehouse to do query acceleration kind of scenario, right? And the data warehouse they were using is actually StarRocks. And despite StarRocks is able to solve the performance problem as a data warehouse, but data freshness still lag a little, right? And also it adds complexity in the data pipeline, right? Because of the additional ingestion task they have to maintain, and they have to do a whole another set of table schema design and index design within the data warehouse within StarRocks, right? And also this is a data governance nightmare because they're duplicating their data out of their Hive data lake and to another place, to another system, right? It's expensive and labor intensive to, it's complex and labor intensive to maintain and to keep data governance good, right? And then they started using StarRocks as the unified query engine, right, to replace what Trino was doing, and also to replace StarRocks as a data warehouse altogether, right, as a unified query layer. Firstly, it streamlined the architecture with one less system to maintain, and raw performance saw a 7-4 times gain, on the same data when compared to Trino. But this is not the point I'm trying to make. The point is that how Trip.com solved all of the slow queries, right? So they were doing what I was saying about materialized view, query the original schema first, and then use materialized view plus, the query rewrite capability to add pre-computation afterward, right? And they were able to solve all of the slow query with only 4 materialized views constructed, right? And the full query rewrite capability ensure there is absolutely no extra work the data user needed to do. The data user didn't even notice, didn't even know that why their query were suddenly running so much faster, right? And with only 4 materialized view and StarRocks core performance, they saw a 10 times plus performance improvement when compared to Trino. Most importantly, all of the slow queries are gone. StarRocks solves your problem, right? It's great for real-time analytics. For mutable data, it helps you ditch your real-time normalization pipeline. It's great for data lakehouse query, right? You can get data warehouse-like performance, so you can actually unify all of your workloads on the data lakehouse without moving your data. Easier data governance, right? But it still comes, the cost of actually owning a infrastructure level software, a stateful software like StarRocks itself, right? First, you have to manage the infrastructure yourself, either on-prem or on the cloud, right? That's something you need to worry about. If you want to scale up or down, you need to manage that, right? The disk space and all of the other configurations comes with infrastructure, right? And also, StarRocks has rudimentary security features, although it has a role-based access control, but it's probably not enough if you're running StarRocks for extremely large enterprise with heterogeneous workloads with many different people, right? And it does not really have a graphical interface. You talk to StarRocks through a command line, and that can be troublesome, right? For some. And also, it has good open source ecosystem integration with other open source projects. But for commercial products, the integration ecosystem integration of StarRocks lags a little bit, right? And here I want to introduce CelerData Cloud. CelerData Cloud is a cloud managed StarRocks with advanced cloud features, right? All deployed in your VPC. How it works is that it has a BYOC, bring your own cloud architecture, right? So on the architecture, you can see that there are two planes. Top is a CelerData Cloud data plane, which is your StarRocks clusters and your own data stored in your own VPC, right? And then there is a control plane, right? Managed by CelerData, resides in CelerData's own VPC, right? Help you maintain all of the clusters that's in your VPC, while you have complete ownership of the StarRocks deployment as well as your own data, right? And CelerData Cloud has a pay-as-you-go cost structure. I charge you by the second when the cluster is up, right? So the fixed cost of trying CelerData Cloud is very cheap, right? It also has advanced security features and access control features such as SSL connection, as well as like column and row masking policy for RBAC, right? And also, CelerData Cloud lets you perform everything that you would normally on the StarRocks, but with a graphical interface, right? Also has advanced monitoring and a dedicated SQL profiling to design for StarRocks, right? And also, CelerData Cloud comes with a bundle of advanced features that StarRocks doesn't have. For example, the multi-warehouse feature, right? It allows you to spawn separated compute warehouses for your different workloads, right? So you can protect your business critical workloads with actual real resource isolation, right? It also has great support for commercial BI tools such as Power BI, right? And lastly, the SLA of CelerData Cloud is guaranteed by the initiator and the maintainers of the original StarRocks project. This is all I have as well for this webinar. You can try CelerData Cloud today at cloud.celerdata.com to claim your 30-day credit card free trial, as well as you can visit CelerData blog for more content like this, and join Slack channel, StarRocks Slack channel. Visit the GitHub page and connect with me through LinkedIn, right? Thank you everybody for tuning in. I'll stay here for a few more minutes to answer any questions you might have. Thank you.